Good afternoon. My name is Sandy Nettles. I'm a professional geologist in the states of Florida, Georgia, North Carolina, Tennessee, and Texas. I own NS Nettles and Associates Inc., and I do business as Ocean Earth Technologies in the Caribbean. I have 47 years of consulting experience in the hydrologic and marine sciences. Today I'm going to talk to you about sea level rise wellfield protection procedures. Sea level rise is a major concern for Caribbean islands as it will impact their groundwater resources, increase coastal storm surge, and reduce their overall landmass. Coastal areas of the islands generally exhibit the major population centers, recreational areas, tourist economic centers, ports, and coastal highways. Encroaching sea level clearly adversely impact each of these venues. Primary importance for island communities are the freshwater aquifers that supply the population and commerce water for drinking and product manufacture. Groundwater is often the primary source of most freshwater development on Caribbean islands. Those islands that do not have freshwater aquifers or springs typically have to develop rainfall capture facilities, desalination methods, or import water via ships. As sea level rises, groundwater reservoirs will be compressed, reducing the volume of the island's naturally stored groundwater. The International Panel on Climate Change has developed three scenarios of global greenhouse gas emissions that they are using to project sea level rise over the next century to 2 centuries. The current level is basically assumes zero emissions, something happening right at 2100. Clearly that's not going to happen. The 4.5 is that assumes that they're stable by 2100. We doubt that that's going to happen. So we're really looking at that reddish, pinkish range from the RCP 8.5 high emission scenario. And this doesn't include some of the potential for the West Antarctic ice sheet slipping into the ocean. The IPCC currently projects 1 to 2 feet of sea level rise by 2100 and possibly as much as 3.5 feet. They believe that there's going to be no less than 29 to 59 centimeters of sea level rise, no matter what happens because of the ice caps and glaciers. Basically, if they cut everything off right now, all the CO2. Copenhagen research went a little bit further back. They estimate about 4.4 feet by the end of the century of sea level rise. And the ice sheets and ocean heat content have multi-century response times, and this can lead to a model drift if the model is not perfectly initialized. This slide just shows you how far off the modeling can be from the actual observations. So it's like every model, they're only as good as the data that gets into them, and we're clearly not quite accurate on or have all the parameters yet to run those models accurately. Most Caribbean islands are volcanic with a central core of volcanoes surrounded by carbonate reef and sand shorelines. Historic lava flows flowing down the sides of the volcanoes create dense rock ridges separated by valleys that occur as spokes around the wheel. Between these ridges, accumulation of volcanic ejecta and ash fill the valleys. The valley fill is typically comprised of fine sand boulders and are very permeable. Rainwater percolates rapidly into the valley, sediments creating freshwater aquifers in each valley. All of these valleys have a freshwater storage capacity based on the aerial extent of the valley, the thickness of the coastal aquifer, rainfall recharge, aquifer storage, and transmissivity measured by an aquifer performance test. Many of these valleys drain directly to the shoreline and are unconfined aquifers. It is rare that these groundwater basins have been adequately determined to determine this valley safe sustained yield. Additionally, it is extremely rare to find a Caribbean island wellfield that has a saltwater intrusion monitoring network installed to control the wellfield pumping schedule or to aid in predicting saltwater intrusion locations and rates. Without such a network of monitoring wells and a wellfield operating program for an unconfined aquifer, these wellfields are highly susceptible to saltwater intrusion, such as occurred in the St. Kitts Basseterre Valley Aquifer wellfield in 2015. Most island coastal aquifers are water table, unconfined aquifers that are recharged by rainfall. Unconfined aquifer well fields should not be designed or operated in the same fashion as artesian aquifers. The smaller storage capacity of unconfined aquifers can be easily dewatered, pumping exceeding rainfall recharge, resulting in mining of the water source. Overpumping coastal aquifers will result in saltwater intrusion into the well field. Now, we want to look at controlling saltwater intrusion advancement into a well field, and this requires an understanding of one, three-dimensional hydrogeology of the groundwater basin. Well construction technology has a lot to do with it. Unconfined aquifer performance testing, a 72-hour pumping test is required to determine the delayed yield effect. Saltwater interface monitor well construction technology, important. Know how to, if you're actually measuring the right location for where the interface is. Wellfield design and operation for coastal unconfined aquifers. They operate again differently from inland and artesian aquifer systems. Fresh saltwater interface monitoring methods. We have a quick way of running conductivity surveys down the wells. Can be done in a matter of minutes, and you can do a number of 30, 40 wells in a day and get you a complete map of the distribution of the fresh saltwater interface. Groundwater level elevations needs to be measured, and you really need to know the depth and location of the fresh saltwater interface. And our experience is that it changes daily with pumping, rainfall, and even tidal effects can move it vertically and horizontally, sometimes large distances. Next, we need to figure the quantity of groundwater that can be sustainably withdrawn. This is the safe sustainable yield and is dependent on several additional factors. You need to delineate the basin's hydrologic boundary, which is the aerial extent of the water, basically the recharge basin. Define the underlying geology and aquifer units, aquifer depth and thickness, presence of dikes or sills, aquatards, stratigraphic lithologies. Determination of the groundwater gradient and range of water level fluctuations seasonally and with pumping schedules. Soils type, distribution and hydrologic characteristics. Rainfall rate and distribution within the watershed. Topography and geomorphology. Evapotranspiration rates and distribution for water tables less than 5 feet below land surface. Datum. In other words, if the water table is more than 5 feet, you really don't have to worry about ET loss. Surface water runoff rates, groundwater recharge rates, groundwater withdrawal locations, rates and periodicity, depth of the fresh saltwater interface below the water table, slope of the aquifer and water table, structural geologic controls that may be affecting groundwater storage and transmission, such as intrusive dikes and faults. Figure 3 is the Corbin principle. This is one of the most important things we have to deal with in the coastal environment or on an island. Florida has the same issue, and this Corbin principle operates here even in the peninsular Florida. And basically it says is for every 1 foot of freshwater you have above sea level, you have 40 feet below sea level. This is very well documented in the islands and in, again, Florida. Classic example of a coastal aquifer well field with saltwater intrusion problems is the St. Kitts Basseterre Aquifer well field. In 2009, Ocean Earth Technologies was contracted to perform hydrogeologic evaluation of St. Kitts Basseterre Valley Aquifer well field. It had previously been investigated and designed by Dr. Christmas in the 1970s, with production wells being drilled in 1988 by the Keir Priestman Associates. Mr. Williams updated and reworked the Christmas data and confirmed Dr. Christmas's safe sustained yield with a computer model. OET geophysically mapped the well field in 2009 using multi-channel electrical resistivity to provide a more complete and detailed hydrogeologic assessment of the well field hydrology and to locate the fresh saltwater interface. OET also investigated the integrity of many of the well field production wells and monitor wells, primarily because most of them had collapsed due to poor construction. Most critical data recorded by the 2009 investigation were the presence of the fresh saltwater interface was recorded to be just below the supply well intake screens across the entire well field area. Saltwater intrusion was already encroaching on the well field from the southwest, southeast, and northeast parts, Only 5 of the safe sustained yield parameters are well documented for the entire Basseterre Valley watershed: the boundary, the topography and geomorphology, rainfall, soil type distribution, and groundwater withdrawal rate, locations, rates, and periodicity. The 5 remaining parameters, the geology and aquifer units, were defined only within the wellfield area, 10% of the watershed, when that included with our 2009 MER mapping. 90% of the remaining watershed is not accurately defined in terms of hydrology, geology, and aquifer characteristics. The geophysical mapping across the Basseterre Valley Aquifer Wellfield site, the southeastern terminus of the Basseterre Valley, revealed the presence of 3 distinct resistivity stratigraphic units across the site. Results of the initial mapping emphasize the importance of accurately delineating the fresh saltwater interface across the watershed and monitoring its location during pumping. An extensive monitor well network should be developed to deal with this sensitive interface issue. Additional water supplies needed to be developed immediately. Construction of new wells should be placed to the north of the airport and in the higher elevations of subbasins A and B of the Basseterre Valley Aquifer. Saltwater intrusion into the Basseterre Valley Aquifer water supply wells was predicted by OET to occur in 2004-2015 if pumping from the wellfield continued at its 2009 withdrawal rates. 2015, the wellfield exhibited a spike in saltwater intrusion and wells had to be shut down and water rationing instituted. This is a map of the hydrologic basin. So here's the Basseterre Valley Aquifer wellfield area, the airport. The valley climbs all the way up to the top of the mountain. This is subbasin B. This is Monkey Hill, kind of separates the 2 bases at the top, and then they join somewhat together, although there are some dikes and sills that we discovered that alter flow patterns within the system. This is a close-up of the Basseterre Valley Aquifer with the well locations. See the ponds, wells, Connery Airport, Taylor, I-1-48, Soho, and W-151 coastline right here. This is the city of Basseterre. This is an example of one of the resistivity surveys that we ran through the well field. You can see the very high resistance area, which is pretty dense rock, a lot of boulders, sand mixed in. We get into the water table. Here's the basically the fresh saltwater interface. We saw the Connery well here. We have 3 units that we identified from a resistivity standpoint. A lot of this has to do with the degree of saturation within the rocks and the sediments. And that profile is across the north end of the well field. And this is where we have some saltwater intrusion, and you can see the upconing here. This is a cross-section of the basically the hydrology of the well field. This is the land surface. These are obviously the casings of the wells. This is where we encounter the water table just barely above sea level. These are the screen sections. Some of them, the wells have a 5-foot section of sediment trap at the bottom. This shows you the line. Basically, this is where we found the saltwater interface. So you can see it's fairly close. And when you're thinking about the Guyman-Herzberg principle, you barely have 2 feet of water level of fresh water above sea level. Well, it's because we're down here about 80 feet thick of water. If we remove a foot, and that's what this says up here in very small print, if we say we drop that another foot of elevation in the water table, this is where that interface is going to be. This is what happened in 2015, is we dropped that additional foot of elevation in the water table as we predicted, and we started getting saltwater intrusion. We combined all the resistivity data and mapped out the distribution of where we see the saltwater at depths, and you can see saltwater is coming in the northeast, southwest, and the southeast. Now this seems to correlate to the break in the mountains. This is obviously coming in through the coastline. This up here must be a fracture in the rock, because we didn't see any other real cause for this water to migrate in here with the testing that we did. Based on our 2009 report, we had entered into a contract in 2016 to do some additional work. We were required to go no greater than 400 feet of elevation, as a previous firm had been under contract to look at everything at elevation from 400 feet up, and they discovered that the aquifers were too narrow and to be economically productive. In 2016, we, under an emergency water resource investigation, we did work on these 3 sites where we were looking at Subbasin B water supply development potential. Subbasin B includes narrow valley formations that are similar to Subbasin A, but indicate they store groundwater at higher elevations than those in Subbasin A. As the Subbasin B exhibits the same geologic stratigraphy as Subbasin A, the water production potential for Subbasin B should be equivalent. However, the igneous dikes that hold the groundwater at higher elevation, plus 19 feet MSL, and creates a thicker freshwater lens, some 700 feet, in Subbasin B, also limit the aerial distribution of the Subbasin B aquifers and therefore their safe sustained yield. The higher elevation of the aquifer in Subbasin B also reduces the potential for saltwater intrusion into the wells in this basin. Results of the emergency water resource investigation of the Subbasin A north of the RLB airport. The data support OET's conclusions from 2009 that the high permeable sediments comprising the Basseterre Valley aquifer prevent significant mounding of groundwater up gradient. A relatively flat water table, less than 5 feet of MSL, is documented within the Basseterre aquifer well field, appears to extend well north of the airport, as shown in MER Transect T1, 5, and 6. This flat water table greatly increases the risk of saltwater intrusion into the existing well field from groundwater withdrawals, even if new wells are located north of the airport. Some of the existing supply wells should then be converted to saltwater intrusion monitoring wells to track the movement of the saltwater interface and permit the water department the ability to more effectively operate and manage water production from the new water supply wells located to the north of the airport. Vertically oriented mid-range resistivity features indicate the porous zones of the Basseterre aquifer in the central region of the Subbasin A may be separated by impermeable intrusive dikes or have low permeable zones that may significantly reduce water production capability in these features. This is a transect through the Subbasin B, the resistivity showing the various 6 units that we were identifying. This is all saturated material here. This is sea level, and here's this intrusive dike that we're talking about, and this is why it's holding up water. So if you can find these in more of the basins, then you have a much better, much safer water supply of fresh water. Recommendations for monitoring the fresh saltwater interface to protect your coastal aquifer well fields. Monitoring the fresh saltwater interface is a 3-dimensional program. The interface can move both vertically and horizontally through the aquifer depending on recharge activity, pumping, and tidal flux. Interface monitor well distribution should consist of transects oriented perpendicular to the shoreline, with each transect having 3 to 4 monitor wells set at 100 to 200 foot spacings from the shoreline to the well field, boundary, or near a supply well. Narrower spacing may be warranted. An additional deep interface well should be constructed 20 feet from each water supply well to monitor for vertical upconing of saline groundwater. All interface monitoring wells should be fully screened from 5 feet below land surface to 30 feet below the initially recorded interface depth as determined by resistivity mapping. Production wells should be run for no more than 24 hours at a time, with a 24-hour recovery time to permit recovery of the local water table elevation. Continuous pumping 24/7 of unconfined aquifers results in a delayed yield effect, removes water from storage, and drastically increases drawdown at the wellhead. This increased drawdown of the water table elevation induces upconing of saltwater at the wellhead. Salinity surveys should be recorded in an interface monitor well on a weekly basis during dry seasons and monthly during wet seasons. Interface vertical and horizontal fluctuations should be mapped with each monitoring episode and compared to previous data to track encroachment so that modifications to the supply well pumping regime can be made to stop the saline encroachment from entering the well field. Supply well distribution should never be established as 2 parallel lines of wells oriented perpendicular to the shoreline. This is a map of the monitoring program that we had presented in our 2009 report for the Basseterre Valley Aquifer. The blue lines, the blue triangles are saline monitor wells. These smaller ones are both water level and rainfall monitoring. So a complete hydrogeologic data collection system. This is a really nice example of how you find a freshwater lens in an island. This is at Timonos Estates in Anguilla. We were actually running this profile to look at the density of the rock. The higher the density is, these higher resistivity. And I happened to notice this change in resistivity as I got near the sea level. I said, well, that looks like a freshwater lens. So I convinced the engineer to let me put in some monitor wells. We installed the monitor wells, let them stabilize for a month because once we drilled into the salt water, it mixes the entire column. But when we were finished, we found this very nice freshwater lens. It was 20 feet thick at the center of the property.
Good day everyone, my name is Lilly Loe. Before proceeding any further, I would like to thank CWWA once again for this opportunity. My study is on climate change and rainwater harvesting for domestic purposes in the Caribbean. The case study of Amityville and Drumley districts in St. Anne, Jamaica. My presentation outline started with the introduction, then on to the research problem and objectives, followed by the conceptual framework of the research problem, then the methodology, the literature review, the results of findings, and then the recommendations and conclusion. I will begin by stating a statement by the Prime Minister of Bangladesh, Sheikha Hasina, which stated, and I quote, "Water is life. It is essential for survival. The future of the world also depends on water. Indeed, we cannot dream of a peaceful and prosperous world without water, but we must not forget that water is a finite resource. If we fail to manage this resource properly, it can cause a lot of human sufferings. Let us all work together for a world where everyone would have equal rights and access to safe water." Now, water is a medium that links every system on this planet, whether it is a natural system or anthropogenic system. And also, the movement of water enables the climate to function properly. Small island developing states are vulnerable to climate change because of the size and location along the tropical belt. RWH, which stands for rainwater harvesting, is dependent on the rainfall, and small island nations would be affected by the change in rainfall. The study area is located in the parish of St. Anne, as seen on the map, on the northern coast of the island. Research problem. The rainfall variability has changed in the region, that is according to Leicester 2018, and rainwater harvesting, which has been practiced by many islands as an augment to water supply, is affected by climate change. It is a challenge for those who are not connected to the centralized water system, like the communities of Amityville and Drumley. However, these two have developed innovative measures to adapt to the situation. Therefore, the main objectives in this study is to examine the impact of the changing rainfall on the harvesting of it, and assess the adaptive strategies that the people in these two districts have been utilizing. For the conceptual framework on the research problem, rainwater harvesting is the focus here. This rainwater harvesting is affected by the natural influence, which is on the left side, and the human influence, which is on the right side. We'll begin with the natural side. For the natural side, the rainwater collected depends on the amount of rainfall. Which depends on the sea surface temperature as an external factor. Moving on to the human side, the human influence, which influences the insufficient water right down to the rainwater harvesting part, is that it is determined by the infrastructure, and then this infrastructure is determined by the cost of whether repairing it or maintenance, as well as the source of funds or income. The rainwater harvested is used for domestic purposes, rather at the bottom of the residence in the households. Apart from that, it is used for farming and livestock. But when going back to the insufficiency, and when insufficient water occurs, the people will have to adapt, innovate certain strategies, and practice conservation. On the other hand, tracking water had to be done, which then gives a feedback loop to insufficient infrastructure. Mixed methodology is used with a 50% of using both qualitative and quantitative data. The data was collected through survey questionnaires and interviews, and then we have the sampling method used is based on the availability of people during the arranged time. After collecting this data, the quantitative data was entered into SPSS, and then the graphs are integrated, whereas the qualitative data was processed in a qualitative analysis as well by transcribing, memoing, developing the imaging teams. For the literature review, there is an emphasis on further studies based on the impacts of climate change to water resources in Jamaica, and highlighted as well by Lester that there is a change in rainfall variability for the region. The rainwater harvesting system is very important for most island nations, but it is exacerbated by climate change. The types of rainwater harvesting methods used in the communities of Harmonyville and Drumley were the rooftop collection, like the one on the left side, and then the ground level collection, which is the one on the right. These are rooftops. Some have overhead tanks, which I'm not able to insert, but these overhead designs use a generator pump to actually transport the water in the cisterns up to the storage tank above the house, and then supplied it into the house. The residents in these two communities used the concrete tank, a plastic tank, and drums. Those are the 50-gallon barrels. From the survey, according to this graph, about 44% used two types of storages. The other 14% in the graph, however, are those used to borrow water from the neighbor's tank and store them in their small water cans. Going on to the rainfall chains. The rainfall chains, according to the survey from the locals, has varied over the years and was worse last year, 2020. The last drought lasted for 3 months, with evidence that 41% from the survey had their water storages run out. According to the rainfall data from the Met Services, which is on the right side, the rainfall for the parish of Senton in 2020 has been the lowest out of all the other years, hence is related to what was observed during the survey. The impacts on water storages being empty by the decreasing in rainfall has been evidenced, as 11% had their storage run out once, according to this graph. About 30% had their storage empty more than twice. So it's an addition from the 11% up to the 20%. Interestingly, 59% had not, and this is because of the different strategies they have utilized to conserve water and have bigger water storage capacities. The main problem during the prolonged drought period is hygiene and sanitation. That is a huge number over there, and then followed by the farming and cost of purchasing the water. The other, on the 11% side, they have all of this like their main issue. They have the farming as an issue, the poor hygiene and sanitation as the issue as well, and then cost of purchasing. So they're equalizing all of these. Therefore, people use these certain strategies as shown in the table, and the strategies are done on a short term, which are referred to as the coping strategies. Similarly, those on the long term are referred to as the adaptation. And there is also a supply side where it is available, and a demand side where it requires effort. Coping including the purchase of bottled by trucked water, borrowed water from neighbors' tank as well. The adaptation include collecting from the community catchment tank in Harmonyville and practice conservation. From the survey as depicted in this graph, majority had been practicing more than 2 coping and adaptation strategies. The reason is due to the usage of water versus the storage capacity. Those with more people consume more water, and sometimes more than what they have stored inside their storage capacity. Therefore, when drought happens, these are the households that quickly run out of water. Those 17%, however, that practice a single strategy are due to certain reasons, such as that household maybe there's only one person living in that household and usage of water is less than the storage capacity. And this include those who are living near the community catchment tank. The resilient techniques used by the people in these 2 communities, however, included managing the usage and practice conservation, which is employed by the majority. 26% have to turn off their taps to ensure there is no leakages, and the other 11% did all of the techniques, while the 17 had responded that they did nothing to conserve water. Interesting. Moreover, in combining the resilient measures and techniques according to the survey depicted in the graph, that 49% did almost everything to ensure they had conserved enough. while the other 14% ensured that gutters were installed properly, and the 9% ensure that there is an increase in their number of storage equipment. 1% practice conservation of water, and 27 do both storaging or properly installing their gutter. Furthermore, Jamaica's National Water Policy and Implementation Plan 2019 has incorporated rainwater harvesting in the Section 10 of the document, which recognizes rainwater as an augmentation of water supply. The implementation part, however, varies for different organizations, such as the Rural Water Supply Limited that utilizes the policy, since it is a state-owned company specializing in improving water supply to areas under the non-utility zones. These are zones which the centralized water system had not reached, and most of these zones are mainly in the rural parts. The Parish Council level, on the other hand, however, is lacking according to the interview information. The recommendations for rainwater harvesting in this study area in Ramilly and Harmony the way forward is in alleviating the issue of water in this community is that starting at the household level, individuals can observe and estimate the level of their water usage during the rainy months and practiced conserving it during the drought periods. That is one. To install extra guttering and storages are needed in some of the houses that need improved rainwater harvesting equipments to harness as much energy as possible. Another point is to use low flush toilets, and those that use generator pumps can utilize the solar energy if it is affordable to them to harness water quickly into the storages. At the government level, the Parish Council for St. Anne could work or collaborate with the RWSL or the Rural Water Supply Limited to aid in the improvement part of rainwater harvesting systems. This include maybe designing economically and environmentally friendly designs that are more affordable and cheaper, and then the second point is that individuals that need extra help need to be identified and assisted. To reduce the impacts of future unpredictable climate change occurrences. Connecting to these areas, water had to be connected to supply and expand the storage capacity of the existing community tanks as well. In conclusion, change in rainfall has impacts on the rainwater harvesting in both studied communities. The main issue, however, is accessibility to water. When there is a need or when it is needed. And a reliable water supply connection would be the best alternative on a long-term basis. And that is where it ends. Thank you very much for listening. Looking forward to your questions. Thank you.